Hello everyone. Today we are starting with one of the most important concepts in modern AI systems, embeddings and semantic search. If you have ever wondered how ChatGPT finds relevant information, or how search engines understand meaning, or how RAG systems work behind the scenes, everything starts here. By the end of this video, you will understand what embeddings actually are, how machines represent language as numbers, why similar ideas end up close together mathematically, and how semantic search finds meaning instead of just matching words. So let's dive in. The fundamental problem. Let's start with something that seems pretty obvious to us but is incredibly difficult for machines. Humans understand meaning naturally. If I say car, automobile, you instantly know that they mean almost the same thing. Now, if I say king, queen, you understand that they are related. If I say doctor, hospital, you immediately see the connection. But for computers, they don't understand any of that. For a computer, the word king isn't a king. It's simply a sequence of character, King. Or even more fundamentally, it's just the numbers stored in memory. The computer doesn't know what a king is. It doesn't know what royalty is. It doesn't know that king and queen are related. So now, this creates the biggest challenge in AI. How do we convert human meaning into something that a machine can calculate? Because the machines are incredible at math, but they're pretty terrible at understanding languages directly. Now let's come to the solution. The solution is to convert language into numbers, but not just any numbers. Numbers that somehow preserve meaning, and that's where embeddings come in. Building a map of meaning. To understand embeddings, first imagine a map. On a real map, Mumbai is close to Pune. Pune is closer to Bangalore than it is to New York. Distance tells us something meaningful. Now imagine building a completely different kind of map. Not a map of cities, but a map of ideas. On this map, dog is close to cat is close to tiger, king is close to queen. Programming is close to software engineering. So, distance now represents similarity of meaning. The closer two concepts are, the more related they are. The further apart they are, the less related they are. But computers can't place words directly on this map. Instead, every word, sentence, or a document gets represented by coordinates. Just like GPS coordinates, for example, dog might become 0.32, 0.41, 0.88. Cat might become 0.29, 0.39, 0.91. Now, do you notice how these numbers are similar? King might become something completely different. So the actual number doesn't matter, but the relationship between them matters. That's the key insight. Meaning becomes geometry. Now the question comes, what is a vector? Let's make sure that we are comfortable with this very important term. A vector is simply a list of numbers. That's it. Nothing scary, nothing fancy. For example, if you say 2, 5, 7, that's a vector. Minus 0.12, 0.38, 9.4, that's also a vector. Now, modern AI systems often use vectors with hundreds or even say thousands of numbers. For example, we have 384 dimensions, 768 dimensions, 1536 dimensions, and 3072 dimensions. You can't visualize as a human that many dimensions, but conceptually, it's just still a list of numbers. So if you want to remember, you can think of vector as coordinates that tells us where something lives in a giant mathematical space. And once everything has coordinates, we can measure distance and similarity. So what is an embedding? Now here's a really important distinction. Every embedding is a vector, but not every vector is an embedding. You may ask why. Because I can generate random numbers right now, like 7.3 minus 4.8 or 15.2. So this value which I generated randomly right now, it's actually a vector, but it means absolutely nothing. What an embedding is a special thing. An embedding is a vector that was learned by a neural network. Now the neural network was trained on enormous amount of data like books, articles, websites, documentation, billions and billions of words. Now, during training, it repeatedly learned patterns such as which words appear together, which sentences mean similar things, which concepts are related. And now, over time, the model built a mathematical understanding of the language. It's not human understanding, but it's basically a statistical understanding. And the result which you receive is an embedding. So, a vector whose numbers encode a meaning, that is an embedding. So, one way to think about it is embeddings are compressed meaning, thousands of words and relationships compressed into a list of number. That is what embedding is. So, if you have to remember just one line, every embedding is a vector, but every vector is not an embedding. A vector which has some meaning behind it, that's what actually becomes an embedding. Now comes the question that how does the model learn meaning? You might be wondering where does this meaning actually come from, right? Okay, so let's imagine teaching a child. You don't explicitly teach the child every possible relationship. Instead, what we do is that the child sees millions of examples and the child starts noticing the patterns. Dogs bark, cat meows, birds fly, cars drive. Now, what happens over time is that the child develops an intuition. Now, embedding models learn something similar. They process enormous amount of text and repeatedly try to predict missing words or understand the context. For example, the cat sat on the blank. The model learns that mat is more likely than an airplane. Now, by doing this billions of times, it gradually discovers patterns in the language. And eventually, it learns relationship like Paris is related to France, and the same way, Tokyo is related to Japan. So, it wasn't explicitly programmed with these facts, but it discovered them through patterns in data. And that is why embeddings capture surprisingly rich meaning. So next comes the what are the popular embedding models. This is a very practical engineering advice. Most AI engineers do not train embedding models from scratch. Training requires like massive data sets and huge GPU clusters. Instead, what we use is that we use a pre-trained models. So think of them as engines, different engines for different jobs. Some popular options include we have OpenAI's text embedding 3 small and text embedding 3 large. These are high quality production models and are widely used in the industry. Sentence transformers, especially All Mini LM L6V2. This is one of the most popular open source model. It's fast, it runs locally, and it's free to use, which is great for learning and building things. Then comes the Cohere embeddings. It's very strong for retrieval applications. Next one we have Google embeddings through Vertex AI and Gemini, and the other ones are like BG models from BAI. Now these frequently rank among the best open source retrieved models. If you are learning, start with All Mini LM L6V2, and if you are building production systems, evaluate OpenAI's embedding models as well. Choosing an embedding model is often like a trade-off between the quality, speed, cost, and infrastructure requirements. Moving on, let's understand what is similarity search. Okay, now every document has become a vector, right? Every sentence has become a vector. Every query has also become a vector. So now the question is, how do we determine which vectors, which of the following, among these thousands of vectors, which ones are similar. Now, this is where similarity search comes in. The most common technique is called cosine similarity. For understanding cosine similarity, imagine two arrows. One arrow is short, one arrow is long. If both arrows point in the same direction, they are still aligned. So, cosine similarity focuses on direction rather than the size. And in embedding space, direction often represents the meaning. That is why it works so well. The cosine similarity score usually ranges between 1 if it is nearly identical meaning, zero point 0.8 if it is strongly related, 0.5 if it is somewhat related, 0 if it is unrelated, and -1 if it is the opposite direction altogether. So mathematically, it's calculated using the angle between vectors. But the intuition you understand is simple. The more two vectors point in the same direction, the more similar in meaning they are. So, what exactly is semantic search? Now, everything starts coming together. Let's compare traditional search with semantic search. Imagine you search for how do I reset my password, but the document says account credential recovery process. Now, traditional keyword search may struggle in this because the exact words don't match. It looks for reset password, and those words are not present. But how semantic search works, it works differently. It doesn't care about it doesn't care about the exact wording. What it cares about is the meaning. The query and the document get converted into embeddings. Because they express the same intent, their vectors end up close together in embedding space. So semantic search successfully retrieves the document. That is why modern AI powered search feels so much smarter than the old school search. It matches meaning instead of the matching words. So, if we come to the complete RAG pipeline, let's put everything together. This pipeline sits at the center of modern AI application. The step 1 is you take your document, PDFs, documentation, knowledge bases, articles, anything. Step 2, split them into smaller chunks. Now the question comes, why are we splitting them into smaller chunks? Because embedding an entire 500-page document usually reduces the precision. Smaller chunks give better retrieval. Step 3. Convert every chunk into an embedding. Now every piece of information has coordinates in the meaning space. Step 4. Store those embeddings inside a vector database. Now tools like Chroma, Pinecone, Vivid, pgvector, Quadrant, these are all the vector databases. Step 5. A user asks a question. Step 6. Convert the question into an embedding using the same model. Step 7. Search for the most similar vectors. Usually the top 5 or the top 10 closest chunks are selected, and this process is called retrieval. Next step, step 8. Send those retrieved chunks along with the user's question to an LLM. This process is called augmentation. Step 9. The LLM generates a final answer, and this step is called generation. So you see, retrieval, augmentation, generation. That's RAG. And now you understand the foundation of almost every modern AI search system. The last line, key takeaways. If you remember only 3 things from today's video, remember these. Number 1, machines don't understand words, they understand numbers. Number 2, embeddings convert meaning into numbers. They are learned vector representations that capture semantic relationships. Number 3, semantic search works because similar meanings end up close together in vector space. Once you understand embeddings, you have unlocked the foundation of RAG systems, vector databases, AI search, document question answering, recommendation systems, and many modern AI applications. Now, in the next video, we are going deep into vector databases. How do we store millions of vectors? How similarity search works at scale? And which vector database you should choose for your projects. See you there.